Hello and welcome back to Unit 3. In this part of Unit 3, we are going to be working examples for 2D projectile motion. The approach to two-dimensional projectile motion problems is identical to the approach for one-dimensional projectile motion problems. Draw a picture, label everything you know, write your grocery list, your list of everything you know, want to know, need to know, and then look at the equations and try to find a way to solve. Often you may need to solve for something else before you can get to the main thing that you're after. And don't forget about symmetry. Symmetry plays a big role in 2D projectile motion problems if they're set up correctly. Particularly remember that at the top, the vertical velocity goes to 0, albeit momentarily. The horizontal velocity is constant throughout the entire motion. Let's get to our first example. In this example, we have a tiger leaping horizontally from a 6.5 meter tall rock at a speed of 3.5 meters per second. And we want to know how far from the base of the rock will our tiger land. Okay. Key word here is horizontally. Okay. That tells you the angle at which this tiger is jumping. Okay. So draw a picture. Now let positive x be to the right, positive y be vertically upward. Okay, I'm going to designate this spot right here as 6.5 meters. And I'm going to let 0 meters be at the ground, so that's the top of my rock. And I have my tiger. Here he is, though those are supposed to be ears, but we're going to go with it. Jumping horizontally at 3.5 meters per second. As we know, this path will be a parabola. This is what I want to know. How far from the base of the rock does he land? I'm going to let the base of the rock be at 0 meters. My acceleration is gravity downward. And my picture at this point is complete. I can now write my grocery list. You know, I don't think this is a good spot for my grocery list. We're going to try again. We're going to move it up over here. So x equals x naught. Vx equals v naught x equals a sub x equals t equals okay. X is what we want to know. X naught we set to 0 because it's our coordinate system and we're free to put 0 wherever we like. V naught x is 3.5 meters per second. That's what horizontally tells us, is the initial velocity is only in the x direction. And because the horizontal acceleration is 0, my Vx is 3.5 meters per second. Vertically, I start at a height of 6.5 meters and I land on the ground, which is at 0. I don't know how fast the tiger is moving when he lands. I do know, however, that his initial velocity vertically is 0 because he jumps horizontally. And in my coordinate system, with up positive, my acceleration is negative 9.8 meters per second squared. Okay, I want to know x. If I think back to the projectile motion equations, this is the only equation I have left that involves x. So I have to use it in order to find the answer to this question. But I can't use it until I know time. So to find time, the first thing I have to do is go use the vertical direction. So I'm going to start by using this equation. Little space short, but we'll make it work. So 0 meters equals 6.5 meters plus 0 meters per second times time plus 1/2 of negative 9.8 meters per second squared times time squared. Solving for t, gives us that t equals 1.15 seconds. Okay, this is an intermediate step I needed to do in order to find the thing I'm actually asked for in this question. To find that, I'm going to use the x equals x naught equation. X is what I want to know. X naught I defined as 0. My velocity initial in x is 3.5 meters per second, and my time is 1.15 seconds. And multiplying that out tells me that the tiger lands 4.03 meters from the base of the rock. In the next example, we have a ball being tossed off of a 30-meter tall cliff at an angle of 15 degrees and a speed of 25 meters per second. And there are a couple things we want to know here. How long is it in the air before it hits the ground? How far from the cliff does it land? And what is its speed right before landing? Okay. So here's my cliff. I'm going to let the edge of the cliff be right aligned with my y-axis. Here's my x-axis. I'm going to let the ground be 0 and y, which allows the cliff to be 30 meters tall, as given in the problem. I'm also going to let the edge of the cliff be 0 meters horizontally. I have my ball being tossed at 25 meters per second at an angle of 15 degrees. And it's going to go up and come down. And as you can see from this, there is no symmetry in this problem. So we cannot invoke symmetry to find our answer. I have one last thing to add to my drawing, and that is that the acceleration is downward and equal to the acceleration due to gravity. I can now start thinking about my grocery list. Okay, filling in what I have. My initial horizontal position I let equal to 0. X is what I want to know for part A, so I'm going to put a question mark there. A sub x, as always, is 0. A sub y in this coordinate system is negative 9.8 meters per second squared. Y naught is 30 meters and y is 0 meters. I know additional information. That additional information has to do with the velocities, but before I can plug it into my grocery list, I have to separate my initial velocity into components. So I'm going to draw myself a triangle. This edge is v naught. This is my angle, theta. I see that v naught y will equal v naught sine theta in this case because it's on the side opposite. And v naught x will equal v naught cosine theta. Okay, v naught is 25 meters per second. Our angle is 15 degrees. If you plug that in, you find that v naught x is 24.15 meters per second. Vx is the exact same value. Again, that is because the acceleration horizontally is 0. V naught y is 6.47 meters per second. And at this point, my grocery list is complete. T is the answer to how long is it in the air is time. How far from the cliff does it land is x. And what is its speed is related to Vx and Vy. So everything I don't have an answer for, I need to find for this problem. Okay. I now need to think of a way through this math. Okay. I know I can't use the x equals x naught equation yet because I don't know time. So I have to work with the vertical equations. I could use the y equals y naught equation to find time first, or I can use the vy squared equals v naught y squared equation to find vy first. That is actually the easier of the two routes because it requires the least algebra and will not require the quadratic formula, which the first method will. So that is where I'm going to begin. So vy squared equals v naught y squared plus 2a sub y times y minus y naught. V naught y was 6.47 meters per second, the whole thing squared, plus 2 times negative 9.8 meters per second squared times 0 meters minus 30 meters. If you work that all out, you get Vy equals plus or minus 25.10 meters per second. But if we think about what the projectile doing, it's starting on a cliff and coming here. And if we look at right before it hits the ground, it's heading downward. So our correct answer is negative 25.10 meters per second. Okay. Now that I know Vy, I'm able to complete part A of this question. The easiest way to do that is to use the Vy equals V naught y plus AYT equation. Plugging in, Vy is negative 25.10 meters per second. V naught y was a positive 6.47 meters per second, plus a negative 9.8 meters per second squared times t, which is what we want to know. Solving for t yields 3.22 seconds. Now that I know t, I can find horizontal distance. So x equals x naught plus v naught xt. X naught I defined as 0. V naught x was 24.15 meters per second. Time was 3.22 seconds. And if you multiply all of that out, the answer is 77.76 meters. Okay. Part C wants to know how fast, or what is the projectile speed right before it hits the ground. This is related to Vx, which we know, and Vy, which we know. However, it is not either of those. Part C wants to know V, the magnitude of it. Okay. To find that, I need to think about what I have going on. I have a triangle with Vx on the horizontal, Vy on the vertical, and notice I have it going downward because Vy is technically negative, and V on the hypotenuse. I can now use Pythagorean theorem to find that V equals, 34.83 meters per second. This concludes this part of Unit 3.